Section 7.5, Properties of Logarithms. When we're doing operations with logarithms, they have their own set of rules, just like exponents have their own set of rules. For example, the first one, log base x of a times b, we can split it up into two separate logs, log base x of a plus log base x of b. Okay, so looked at it backwards. Anytime we're adding two logs of the same base, both base x, we can change that into a single log, right, with a times b in the parentheses. For dividing, it switches to a minus, okay, and vice versa. So if we have two logs subtracted, we could write it as a single log a divided by b. And lastly, if we have a log where something is raised to a power, we can take that power and move it to the front and turn it into m times log base x of a. Now, I suspect that was a bit confusing, but really it's just about applying these properties in order to solve equations. So for example, let's say we have log base 3 of 81 times 27. I don't know what 81 times 27 is. However, since we have a multiplication sign here, we can split this up into two separate logs, log base 3 of 81 plus log base 3 of 27. And now we can solve each of these individually. So let's send them both equal to x. 3 to the x power equals 81. 3 to the x power equals 27. This is just solving logs like we did previously. Break each of those numbers down. So if we did a factor tree on 81, we would get 3 to the 4th. Factor tree on 27 would give us 3 cubed. So here we can see x is just 4. So this whole thing right here equals 4. This whole thing equals 3. 4 plus 3, 7. This second one, log base 5 of 32 minus log base 5 of n equals log base 5 of 4. Subtraction, we could rewrite as addition and just put both of these inside a single log. Log base 5 of 32 over n equals log base 5 of 4. These are the same, which means we can get an equation. 32 over n equals 4. Cross multiply, solve it out, n equals 8. In number 3, we have a log base 5 of 25 squared. Anytime we have an exponent attached to something inside this log, we can take that exponent and move it out front. And it's going to become 2 times log base 5 of 25. So the 25 lost that exponent, and it ended up out in front. Now we can solve this part. Let's say we set it equal to x. 5 to the x power equals 25. X is obviously 2, and then we have to do 2 times 2 to get our answer. If we didn't split it up, it would still work. 25 squared is 625. 625 breaks down to 5 to the 4th power. Now if we set this equal to x, we would have 5 to the x power equals 5 to the 4th, and we get that same thing, x equals 4. Okay, some of these numbers, when we square them, are going to get really big. So it's easier if we know what to do with that exponent where we take it and we move it out front. Okay, we can also go backwards, like in this next one. We have a whole bunch of log base 7s here. Let's see if we can make these into an equation where we can just set those parentheses equal to each other. So for our first step, we have a 2 out front. I'm going to do the opposite of what I just did in the previous problem and move it to a squared up there. I also have 2 logs that are added together. Adding means multiplication if we're going to combine them into one log. So we have log base 7 of x squared, log base 7 of 27 times 3, that's 81. So now we have x squared equals 81. Square root both sides. Remember, anytime we square root, we get plus minus. However, if we plug in that negative, that's an extraneous solution. The only one we care about is the positive one. Let's take this one step at a time. Log base 6 of x plus log base 6 of x plus 5 equals 2. No log base 6 on the right side, so we're going to have to deal with that. But to start, let's combine these 2 logs on the left side. There's a plus in between them, which means we can multiply those 2 and make it just a single log base 6. So x times x plus 5 inside that single log equals a 2 on the right. Let's get rid of this log altogether by doing 6 to the 2nd power, and it's going to equal what's inside this parenthesis here. X times x plus 5 equals 6 squared. That's our equation. Move everything to the left. Factor it using earmuffs. We get x plus 9, x minus 4. Two answers, -9, +4. Obviously, if we plug in this -9 right here, that's extraneous. We throw that one out, x equals 4. Here it gives us a decimal approximation for log base 4 of 3. Tells us it's equal to 0.7925. We're going to use that to approximate these next two problems. So to start, log base 4 of 768. I don't know what that is. However, it's telling us what log base 4 of 3 is. So let's divide that 768 by 3. So if I take out a 3, it's 256 times 3. That's going to help us. Before we do anything else, okay, so I've split this up. 768 is 256 times 3. And now that we have this multiplication sign here, we can split this up into two logs. Log base 4 of 256 plus, okay, instead of that multiplication, log base 4 of 3. Now this 256, let's solve this out. 4 to the x power equals 256. Do a factor tree on that 256. We'll find it turns into 4 4s. So x equals 4 over here. And then this we know equals 0.7925. So our answer is just those two things added together, and we get 4.7925. This next one, log base 4 of 27. 27 I can rewrite as 3 times 3 times 3, or 3 cubed. We have an exponent up here. We can move it out to the front. Make this 3 times log base 4 of 3. And again, we know what this equals. It's 0.7925. 3 times 0.7925 gives us our answer, 2.3775.